Hi, my name is Mustafa, and today I'm presenting fraud and data availability proofs for FC21. This is a joint work with Alberto, Sonnino, Vitalik, Buterin, and Ismail Khoffi. Now, to understand the motivation for this work, we have to talk about a trade-off in blockchain systems, and that's the trade-off between how decentralized that blockchain system is and how scalable it is. To understand why this trade-off exists, we have to understand the two different types of nodes that can exist that validate blocks on the blockchain. So there's full nodes, which is short for fully validating nodes, and those are the standard nodes that you might, for example, run if you download the Bitcoin Core node software. And these nodes, they download all the blockchain data. That includes all the blocks in the blockchain and all the transactions in those blocks, and validates those blocks according to some transaction or state validity rules, and checks that every single transaction in every single block abides by some rules. For example, you can't spend other people's money, or you can't spend a transaction output if you don't have the correct signature for for the key belonging to the output. So with full nodes, if you have a 51% attack against the blockchain, i.e., the consensus of that blockchain is malicious, and let's say 51% of those miners are malicious, then the worst thing that you can do with the 51% attack is either censor transactions or reverse blocks. A 51% attack cannot, for example, create blocks with invalid transaction that, for example, steal funds or create money out of thin air. Because if they do that, then what will happen is that those full nodes will verify those blocks and immediately reject them because they're invalid. Now, the other type of Bitcoin or blockchain node there is a light client. And these light clients are basically nodes that don't have the resources to download and verify every single block in the blockchain. And so those nodes only download the metadata for the block, what's known as the block header. They don't actually check that the data of the block is valid, and they don't check that the transactions are valid at all. They simply assume they're valid, and they assume that there is no 51% attack against the chain, and that the consensus of that chain is honest in only generating blocks that have valid transactions in them. Now, this is a completely different threat model than full nodes, because if you run a light client, then a 51% attacker could actually create blocks that include invalid transactions that don't abide by the transaction validity rules of that chain, and can trick you into accepting blocks that, for example, print money out of thin air or steal people's money. On the other hand, the full nodes would reject those blocks, so you basically end up in a hard fork where the light clients and full nodes would disagree on which is the correct blockchain. Now, if everyone starts running a light client, then this significantly decreases the decentralization of the chain, because it significantly increases the incentive for doing a 51% attack. Because whereas previously a 51% attack could only reverse or censor transactions, if everyone run a light client, then 51% attacks could actually steal money or print money or change the rules of the money supply. So a very important question is, how do we actually reduce this trade-off? And in order to reduce this trade-off, we have to ask the question, how can we make light clients reject these invalid blocks that contain invalid transactions, so that they don't have to assume that the miners are honest, and therefore the light clients could have almost the same level of security as these full nodes in rejecting invalid blocks. And this is the aim of this paper, using fraud and data availability proofs. So the basic idea of a fraud proof is that if you consider that a block consists of two components, the block header and the transaction data of that block, where the header could, for example, include the Merkle root of that transaction data, then the idea is that a full node can, if they detect an invalid transaction in that block, they can send a proof to the light client, a very succinct proof to the light client, to prove to them that block contains an invalid transaction, which consists of simply that invalid transaction and some other data that we will discuss in a moment. Now, the original Bitcoin white paper actually mentions a similar idea called alerts, which are basically messages that a full node can send to a light client to alert them that a block is invalid. And that would prompt the light client to basically download that block and check whether it's valid or not. The problem with this is that it's vulnerable to denial of service attacks, because you can basically run a bunch of full nodes to send an alert for every single Bitcoin block or Ethereum block or any kind of blockchain system to block to every single light client, and that would basically prompt the light client to download the whole blockchain and validate the whole blockchain again. And so in that scenario, if you do that attack, then the amount of resources that you need to run a light client would basically be equivalent to a full node. And so that's basically back to square one. Now, recently, a few years ago, there have been some ideas on compact fault proofs, which instead of sending alert to a light client to alert them that entire block is invalid, you basically alert them to say that this specific transaction in this specific block is invalid, and here's a proof for that, and the proof for that is different depending on which way or how that transaction is invalid. So, for example, if it's spending an input twice, for example, that a previous transaction has already spent, then the fraud proof would consist of that previous transaction to prove that that input has already been spent. And these early proposals require a different type of fraud proof for every single type of way that the transaction violates the rules. But we can improve on this by generalizing the blockchain as a state transition system, which is what blockchains like Ethereum already do. And so if we assume that there's a function called transition, which takes as input the state of the transaction and returns a new state, then you can basically imagine that every single transaction in the block modifies the state of the blockchain in some way. And basically we need to prove that if some transaction modifies the state in an incorrect way, then we have to prove this succinctly. Now what we can do is we can represent the entire state of a blockchain as a Merkle root, and that basically allows us to commit to the state of the blockchain in a very succinct way. And blockchains like Ethereum already do this using Patricia trees. But we can also use sparse Merkle trees, which are basically trees with a very large number of leaves. So, for example, if you wanted to have a 2 to the power of 256 leaves, which is every single possible SHA-256 hash, then you would basically initialize the tree with that many leaves. But the tree is still efficient to compute because most of the leaves are empty. So you can basically very efficiently compute the root of that tree. Now, if you imagine that you basically store the state as a key value store, then you basically say to access a key k in the tree, you hash k, and then you access that specific item in the tree. You convert the hash to an integer, and you access the index of that integer in the tree to get the value for that key. So once we've represented the entire state of the blockchain to a Merkle root, you can assume that there's a state root transition function. So instead of a function to make transitions to the state itself, you can imagine that there's a function to make transitions to the root of the state. And so you imagine a function called transition root that takes as input the root of the state the transaction itself and some witnesses to that transaction. Now, the witnesses to a transaction are basically the Merkle proofs of all the parts of the state that that transaction accesses, either reads or writes. And this effectively provides a execution trace for every single transaction in the block. If you imagine that every single transaction in the block changes the root of the state in some way, that basically allows you to create an execution trace. So therefore, if a specific transaction is invalid, it's very easy to generate a fraud proof for that. You basically have to provide the transaction itself, the pre-state root, the post-state root, and the witnesses for that transaction. And that's basically the fraud proof. So you can send that to a light client, and they can very easily check by recomputing or re-executing that specific transaction on the state witnesses that that transaction is invalid. And the light client can do this by only knowing the parts of the state that that transaction accesses, rather than needing the state of the entire blockchain. Now, this all sounds well and good so far, but there's a massive problem with this. What could happen is that a malicious miner might come along and publish a valid block header that light clients download and accept as part of their chain. But the malicious miner might not actually publish the transaction data that corresponds to that block header. And if that transaction data includes an invalid transaction, then because they haven't published the data, then a full node would not be able to download that data and generate a fraud proof. And therefore the light clients would have accepted the block header corresponding to an invalid transaction data that is also missing. What we ideally need is a way for light clients to guarantee or check that when they download a block header, the data behind that block header has actually been published to the network by the miner and is available to those full nodes that can generate fraud proofs. And that's the purpose of data availability proofs. Data availability proofs rely on a primitive called erasure coding. And with erasure coding, the basic idea is that if you have a file or some piece of data that is, for example, X pieces long, what you can do is you can apply an erasure code of that data to extend that data to 2x pieces long, so you're doubling the size of the data, and we call the latter half of that data the extended data. With this extended data, or with this extended file, you can recover the whole data from any X pieces, or any half of the data. And so what that means is that if you lose any half of the data, you can recover the entire data from the other half, regardless of which half of the data you lose, even if the pieces are not in order, for example. So what you can do with this is, instead of requiring miners to commit to just the original block data or the original transactions, i.e. the Merkle root of the block transactions, we can require miners to commit to the Merkle root of the original data and also the extended block data, which is the erasure code of the block data. And under this scheme, in order for a miner to hide even a single byte in the block, or a single piece of the block, they have to hide at least 50% of the block. Because if they only hide one byte or a few pieces of our block, then anyone can come along and reconstruct those missing pieces from the rest of the block. This is very useful for light clients because what they can do now is they can randomly sample different pieces from that block to test how available it is. If we assume that the miner is malicious and has withheld half the block because they want to hide any piece of that block, then if a light client randomly samples a piece of that block, there's a 50% chance of landing on a unavailable piece that the miner has not published. And if they land on an unavailable piece that they cannot download, then the light client knows that the block is not available and therefore can reject that block header. So after one sample, there's a 50% chance. After two samples, there's a 75% chance of detecting invalid block or unavailable block. After three samples, it's 87.5% chance, and so on and so forth, until if you keep doing more samples, you get a very high probability guarantee that a block is available, or that you have not landed on an unavailable. There's no unavailable pieces in that block. Now, with this scheme, clients gossip these pieces to other nodes, such as full nodes, to enable full nodes to recover the entire data from the different pieces. Similar to how BitTorrent or IPFS or other file sharing systems work, where they have different peers sharing different pieces of files with each other. For this scheme to work, there has to be enough light clients in the system, making enough sample requests to be able to reconstruct the entire block, and we'll discuss this in a second. The problem with what we've described so far is that what could happen is that the miner could incorrectly generate or compute the erasure code. They could simply commit to gibberish for the extended part of the block. If you want to prove this to a light client, then you basically have to send them the entire original block data so that the light client can recompute the erasure code for themselves to check if it's correct. And that's basically back to square one, because we're trying to avoid light clients from having to download the entire block, because that requires them to have the similar resources to a full node. To fix this problem, we can use multidimensional erasure coding. And in the paper, we use two-dimensional coding. And the way that works is that you have to first of all arrange all the pieces of the block data into a square. So in this example, we've arranged the original transaction data into a 4x4 square with different rows and columns. Then what you do is you individually erasure code each row and column in that square, so then you have an even bigger square. So in this example, we've extended a 4x4 square into an 8x8 square. And once you do that, you require the miners to commit to the Merkle root of each row and column of that square in the block header. And to generate a fraud proof, to prove to someone that this code has been incorrectly computed, instead of having to send them the entire original block data, you only have to send them a single row or column from that block to show them that a piece of some of that data that has been erasure coded is incorrect and therefore must be rejected. With the two-dimensional scheme, and in the paper, we specifically use Reed-Solomon codes with a 1-to-1 coding ratio, message to coding ratio. The miner has to hide at least 25% of the square in order to make it so that the block cannot be recovered. So with the scheme, if you want to have a 99% probability guarantee of that the entire block data is available, then you have to make 15 sample requests. If you make 30 sample requests, you have a 99.99% guarantee. Now this significantly increases the cost of generating an invalid block or tricking a specific light client to accepting an invalid block. Because if you do 15 samples and you only have a 1% chance to accept invalid blocks, then a miner has to effectively, if they're using proof of work for example, mine 100 useless blocks on average in order to generate one block to fool a specific light client. Now, one important consideration with the scheme is that the miner might only release pieces as clients ask for them. So obviously when the block is first published, um, or when the block header is first published, then none of the block has been published yet, or none of the transactions in the block have been published yet. Then light clients will start sampling different pieces of that block, and then what a miner could do, it could slowly respond positively to the first few sampling requests to that block until it reaches a certain threshold, such that if it releases any more samples past that threshold, then the entire block could be recoverable. And so I call this selective releasing of the pieces. And the number of light clients that can be fooled in this way is dependent on how big the two-dimensional square is and how many samples each light client is making. So for example, in this table it shows that if each light client is making 10 samples each, and the square is for example 64 by 64, then you can fool the first 2,000 light clients into thinking that the block is available when it's not. Now, whether this is reasonable or not, it really depends on how big your network is. So, for example, with the Bitcoin network, there's more than 1 million light clients running in the network, according to at least Google's Play statistics on how many people have downloaded a popular application called Bitcoin Wallet, which runs a Bitcoin light client. But this can be prevented if you assume an enhanced network model where clients can send requests anonymously, and those requests are received by the full nodes and block producers and miners in a uniformly random um, order. And one way you can achieve this, for example, is using a mixnet. And what this effectively causes is it makes it impossible for the full nodes and the miners to be able to link specific sample requests to specific light clients. And so therefore you cannot fool specific light clients into thinking the block is available when it's not, just because they were the first 2,000 light clients, for example. Now, if you analyze or think about what are the security assumptions with fault proofs compared to without using fault proofs for light clients, or as they refer to in this table, SPV clients, which is what they're called for Bitcoin. So this table compares it specifically for accepting validated blocks. So for full nodes have if you use the full nodes as the base for our security assumptions, full nodes are the most secure in the sense that you cannot cause a full node to accept invalid blocks, assuming that the code for that full node is correct and the computer is secure, because the full node validates the blocks themselves. So if they come across an invalid block, then they will not accept that block into their chain. Now, with standard light clients or SPV clients, because they don't validate the blocks, they assume that the consensus is honest in the sense that they have only generated blocks that contain valid transactions. Now, full nodes don't assume that. It's a common misconception that full nodes assume that the consensus is honest in that they only generate valid blocks, but actually they only assume the honest majority assumption, not for checking that the state is valid, but for making sure that there is no double spending attacks, or there's no attacks where transactions are being censored. So full nodes only rely on this assumption for censorship resistance, not for state validity. Whereas SPV clients, they do rely on this assumption for state validity, and they do rely on also a synchronous gossiping network for the state validity, because they have to know what the longest chain is in the network is in the first place to know what block is in the longest chain, to know what to know what block is apparently valid according to most of the miners. Now, full nodes also assume a synchronous gossiping network, but they only assume this to know what the longest chain is to be on the right chain for censorship resistant purposes, not for state validity purposes, to be clear. Now, if we introduce fraud proofs into the mix and allow light clients to use fraud proofs, then what that effectively does is it replaces this honest majority assumption for state validity with a much weaker honest minority assumption, an assumption where you need a minimum number of light clients making enough sample requests such that they can collectively reconstruct the entire block. I'm not going to go into too much detail into the performance, but you can check out the full paper if you're interested. But in a nutshell, everything, including the fraud proofs and the block headers, are in the order of a few kilobytes, including the computation times are also in the order of a few milliseconds. Now, the most related work to the work presented here is a proposal called Coded Merkle trees, which was first presented last year at FC20, and this scheme builds on our work. The way that it works is that it proposes a Merkle tree where each layer of the tree is erasure coded using a LDPC code. And the coded Merkle tree scheme is more order optimal than the scheme presented in this paper because the coded Merkle tree scheme only requires a order 1 commitment in the block header, which is simply the Merkle root of the coded Merkle tree. Compared to our scheme, you have to commit to the Merkle root of every single row and column in the two-dimensional erasure code, which requires an order square root block size commitment in the block header. However, the coded Merkle tree scheme has higher constant costs because in order to sample a piece from the block, that has higher costs because the size of each node in the Merkle tree is now bigger because each layer in the tree is erasure coded. So, which scheme is more efficient depends on how big the blocks in your blockchain is. So, if we compare it with similar parameters where each piece of the block is 256 bytes big, then the coded Merkle tree schemes outperforms the scheme in this paper if the blocks are greater than 50 megabytes. We have some further analysis in the paper, but in the best case scenario, if you use the smallest possible bytes per piece, which is 32 bytes, which is equivalent to the size of the SHA-256 hash, then in that circumstances, the coded Merkle tree schemes is more efficient for block sizes greater than 6 megabytes. However, our scheme is more efficient if you compare the overall costs for smaller block sizes. Thanks for watching this presentation. If you have any questions, then don't hesitate to email me. And if you're interested, you can dig into the code, which has been published on GitHub if you follow the links in these slides.